I was supposed to start corrosion, but I'm not going to start it right away. However, tomorrow we've got 2 people presenting, right? And I haven't gotten about a bunch of volunteers, so I'm handing around a sign-up sheet for this Friday, Monday, and Tuesday. And there's 9 slots. And there's only 7 of you left after 2 of you do it. Is there anyone who couldn't do it by then? It gives you a whole weekend. It's only a 10-minute talk, right? No, seriously, if there's a problem.
How mandatory is the PowerPoint?
It doesn't have to be, you can do the board.
Okay.
I mean, a really good lecturer doesn't need a PowerPoint, okay? That's what my slide said. Okay,
PowerPoint it is.
and most, well,
Universally.
I may critique some of your PowerPoint, although most students are getting better at PowerPoint. There's not as many eye charts and stuff. But, and you can switch with people if someone takes up all the slots that you like. You can switch with somebody. But I actually think it's best if you get this requirement out of the way. Okay, early. Procrastination is not a good thing, guys. Anyway, so what? Okay, I was going to tell you when we talked about electroslide welding, and I showed you electroslide welding. But it turns out if you went down to Quonset Point, anybody been? Have you been down to Quonset Point?
Mm-hmm.
Okay, so what is Quonset Point? Tell them what it is.
It's an old Navy base.
Yeah, it's where they invented Quonset huts.
Yep.
In World War II, right? That's why they're called Quonset huts.
That's claim to fame, basically. There's nothing there now. There's Air National Guard. That's it.
Well, there's Electric Boat has a big fabrication facility. And they weld up the outside shell. And they don't, the cylindrical shell of the subs is made at Quonset Point indoors, so they don't have to worry about the weather. But even more important, they don't have to worry about the satellites from up above that could take a picture and measure the thickness of that steel hull. If you know the diameter and the outside wall thickness, you can estimate, because it's just a ring-stiffened cylinder, and you can figure out the diving depth, okay, which is classified, and which I actually do know, but I can't tell you. But most of you probably know it better than I do. Plus, it's made a change in the last 25 years. In any case, what they do is they actually use MIG welding, which is a wire-fed, gas-shielded process. But they weld the cylinders in a vertical position, and they make 4 welds at a time. So I just took this cup to kind of show you, a vertical weld in a cylinder. And they will make 4 at a time. And even though vertical welding is slower, 4 welds is not slower than 1 horizontal weld. Okay, horizontal welding is, or flat position welding is faster, but you get more distortion, and they're looking for low distortion, and they're also looking for speed of fabrication. So here's my model of how they do it at Quonset Point. So you didn't actually get into Quonset Point. You were actually stationed at the sub-base or the.
I just grew up in Rhode Island, so I went there for air shows and stuff.
Okay, so you weren't there. You weren't stationed there.
No.
They do have an underwater system center down somewhere around there. The Navy's
That's in Newport, isn't it?
Yeah, it's in Newport. It's somewhere close, not too far away, right?
Everything in Rhode Island.
Everything's in Rhode
It's all
Island.
close to each other. It's all 15 minutes away.
Okay. Great, thanks. The other thing is, before I start corrosion, I wanted to finish up and tell you one of my great failures when I tried to estimate the cost of building the new Alvin Hall. And this book goes through about 15 or 20 pages of all the options. We could have purchased the steel hull from the Soviets. They had a couple of them they weren't using, okay? They had the right size. We might have been able to use the C-cliff, but as I told you, we couldn't use that because you'd have to have a whole new surface fly ship because you didn't have the crane capacity for the larger hull of the C-cliff. Anyway, they looked at all the options they could, and even reusing the old titanium hull from the original Alvin, but rebuilding that would be almost as expensive as building a new one. One of the problems in the whole thing, there were like 32 people on this committee, I was the only one who had any fabrication experience with titanium. All the other people were marine biologists and things like that who wanted to use the ship. And so when it came, one of our charges was to tell the National Science Foundation whether they could build a new Alvin for $25 million. Now Woods Hole, who had built the first Alvin for the Office of Naval Research and had been maintaining the Alvin for years, actually provided us with a comparison of their estimate of what it would cost to build a new Alvin. And of course, you know, they have a vested interest in coming up with a low cost projection, right? And they came up with $6.5 million. And this is, in the handout I gave you yesterday, this page comes from there, but it's, and it's still, even if I blow it up, it's a little bit of an eye chart still. But it's basically got, it breaks everything down into structural and ballast, and there's more down here, instrumentation and stuff. Well, I'm not an expert in all of this stuff. How could I? And you have to remember, you're now transitioning from being an officer or an engineer to, you're going to become a manager of engineers, okay? And you're going to have to be the one making decisions when people come and give you a load of bull like Woods Hole gave us, okay? And so how can you analyze something this complex in 15 or 20 minutes, okay? And be able to tell the people that they're full of shit, okay? Not in those words, but maybe in more forceful words, okay? But a little more content. So they had just built the Jason II, which was an underwater autonomous vehicle, but it had a tethered cable to it, right? And it turns out these were the costs. They started out, this is their chart from Woods Hole. The weight of each one of these components. This is an unmanned underwater autonomous tethered vehicle, the Jason II, doing research. And the cost, and they had paid for the Jason II $2.3 million. That was a fact, okay? And they figured they could build the new Alvin for $6.5 million. Now the interesting thing, I just looked at the bottom line here and I saw that the weight of the Jason II was 7,200 pounds and the weight of the new Alvin was 33,000 pounds. And I calculated that the cost per pound is sort of like buying hot dogs, right? In the grocery store. The cost per pound of the Jason II, an unmanned, tethered, autonomous vehicle, was $320 a pound, and they were going to build something that was almost 5 times the size, that was manned, untethered, and had to be man-rated, so there's lots of safety stuff that goes in that you don't have you lose a Jason, you buy a new one, right? And they were going to do it for $193 a pound. So this is your discount building program here. I said, makes no sense, folks. Okay? And I also, you know, they're not paying you anything to serve on this committee. So I looked at it and said, well, if instead of $320 a pound for the Jason, I figured $400 a pound, that worked out to $13.5 million, not $6.5 million. We knew the NSF had said their maximum was $25 million that they had available. And so I said, okay, so let's take $400 a pound, and I don't have to worry about all this fluff up here, right? The theme here is how much does it cost per pound, folks, okay? And I said, well, let's just raise $13.5 million, let's raise it up to $16 million. And $16 million, I could do that in my head, it was less than $25 million. And I said, you can buy a second Jason, just, you know, on the side. And I said, you should have enough money to do this, okay? And I think that's probably what it's, something like that, maybe nicer words in the report. So, how close was I? This was in 2004. And I didn't tell you, but Mildred Firebaugh, who was a 13A grad, who had been a captain in the 1980s and had, late 80s, had designed the Seawolf. He was head of the Seawolf design program. And then when the Seawolf was being built and had its problems, he was chief engineer of the Navy. And then a few years later, he was the vice president of Electric Boat, okay? But I knew Millard reasonably well, having met him when he was on the design team for the Seawolf. And I didn't know it, but Millard was the one, these reports have to be peer reviewed. And so Millard was the one, he was the only one, if you look at the peer reviewers, like there's 4 or 5, all the rest of them were my marine biologists and stuff. So Millard was reviewing me. Okay, we kind of knew each other. I didn't know he was the reviewer, but anyway, so he passed off and approved my analysis, which is not much more sophisticated than I just told you. And the final price, what happened in 2000, between 2005 and 2007, the Chinese just started buying metals all over the world, and the price of most metals went up a huge amount, okay? Like a factor of 2. Well, if the price had always been, last I heard, the price of building the new Alvin was $37 million. So my $16 million was closer than their 6.5, okay? But it was still a long way from reality. And part of the problem, one of the reasons I'm telling you this is, most of the infrastructure, the forging capacity, the machining capacity, the rolling capacity that had built the original Alvin hull in the early 70s and the Seacliff hull at the same time, it was gone. It had been mothballed. It had scrapped. The industry was not building anything out of titanium, heavy wall titanium. So essentially, when they went to industry and said, oh, you've got to do titanium, they just said, we don't know how to do it. All those people are dead, retired. And we're just going to put in a safety factor in there because we don't know what we're doing. And we're liable to, have a number of failures. Even though we had built things in the 70s, now we're talking 40 years later, and none of those people were around. And you run into those types of problems all the time. Does anybody know the battleship Iowa, where the gay soldier blew up his partner in the turret? Was that the Iowa down near Puerto Rico or somewhere in the Caribbean? Anyway, he set off one of the shells, on a 16-inch shell, in one of the turrets of the 16-inch guns and stuff. And the Navy went to repair it. And I remember I was working down at David Taylor that summer, and they asked me, well, how do you weld 16-inch thick armor? And it turns out we welded a lot of it in World War II. But in 1980s, those people were all dead. And there was no welding procedure for 16-inch thick armor plate. And the Navy did not know how to weld 16-inch armor plate, so the ultimate solution was to not repair it. Okay? So what do you need? You've got 3 turrets, you lost one, you still got 2/3 of your firepower. And the last time anyone used one of those, I think was, they were lobbing shells into Syria or something back in the 70s or something. But they had a huge stockpile. All the shells they had were from World War II. Okay? I mean, no one's making 16-inch shells and powder bags and stuff. Anyway. And they just keep your powder dry, as they say. Anyway, but there have been a couple of cases that I've been involved in where, we learned how to do things half a century ago, we knew how to do it, and we don't know how to do it anymore because the people all retired. And I mean, NAVSEA and the Air Force and everybody else is well aware of this. That's why they try to keep programs limping along so you can keep the workforce. Because you can't just kind of shut down production for 20 years and come back and gear it back up. You lose all the built-in expertise. Okay, any questions? I thought that those were some decent stories to talk about, and that you're going to be faced with similar types of questions. You're going to have to look at estimates that are probably about as bogus as they possibly could be. And you're going to have to figure out a logical way to say, this doesn't make any sense. Okay? And it was clear that Wood's whole estimate made no sense. But there was not a single marine biologist in the room that could have figured that out. Okay? I guarantee you. They could not figure out what type of milk to buy at the grocery store. Okay. They could do a lot of good marine biology when it came to estimating costs of fabrication. Now, corrosion and marine engineering is what this part of the course is supposed to be. And you have to kind of start, well, first of all, this is not a typical corrosion course. We had one of the world's experts in corrosion, Ron Tennyson, who's now about 75, and he retired at age 62 in 2002 or so. And we still have Ron Ballinger over at Nuclear Engineering, who was one of Ron Tennyson's students, but Ron Ballinger is older than I am. He's about 70, so he won't be around forever. And if you don't know Ron, you might want to go meet him. He started out before he got his PhD. He was a chief in a submarine reactor room. And when he first came here, I remember I was a new young faculty. He had the language to go with it, okay? It was sort of out of place at MIT, but I mean, whew. He was colorful. He's still colorful, but he's calmed down a bit. In any case, you have to ask what corrosion is, and if you took an MIT corrosion course, and a lot of the 2Ns did, I don't know it was required by NAVC, but certainly, I told you the Navy's the corrosion leader. And they would take you through things like the TOEFL equation and these things, just like doing an integral or solving a differential equation. You know, it's something you have to learn to do at the university, but you'll never do for the rest of your life, okay? So, I was around 2004 or so, a couple of years after Ron had retired, I was telling one of my stories and it had something to do with corrosion, and I looked out and none of you guys knew what I was talking about. It was pretty simple corrosion stuff from my point of view. I said, you need a course in corrosion. And so I volunteered to teach the course if you guys would do the work, okay, and that was the deal. And so that's where we actually started the presentations. And the presentations originally were supposed to be the corrosion I have experienced in the Navy, okay? And everyone had a story, okay? And we kind of tied it together. And the way I tied it together, which you're going to see here in a second, is I used two books on the forms of corrosion. Ohio State University has a corrosion research center. It's actually called the Fontana Research Center. This book is Corrosion Engineering by Mars G. Fontana, who's passed away, but he probably wrote it originally in the 40s. Well, it says 67, 78, and 86. So, but anyway, they've had a corrosion research center, a very well respected corrosion research center since the 40s. Ronald Tennyson was a postdoc at Ohio State. He was a Penn State grad and went to Ohio State for a postdoc and did stress corrosion cracking. And a lot of the top corrosion engineers in the country have come out of Ohio State. And the outline of this book, and by the way, Jerry's posting about 50 articles from last summer on the Stellar site. And a lot of this book is copied, and I put that in there. You also have part of this book. But the outline of Fontana in the index, or the table of contents, is the 8 forms of corrosion. And then there's this book by C.P. Dillon, as the editor, of Forms of Corrosion Recognition and Prevention by the National Association of Corrosion Engineers. And they're not the same 8 forms, okay? And so you find there is no standard way of looking at corrosion. Okay, so I kind of go back in a typical MIT way of asking the question, what is corrosion? And what's this thing hanging up on me again? There we go. What is corrosion? And it depends on who you are and what your perspective is. The dictionary says it's a gradual natural chemical process. Now, what do we mean by a gradual process? Well, remember 3 Mile Island? You guys are nooks, so you've heard of 3 Mile Island. after 3 Mile, and about 2 years after 3 Mile, there were 2 reactors there in Harrisburg, Pennsylvania. One of them had a meltdown and the other one didn't. And GPU Nuclear, General Public Utilities Nuclear, wanted to start up the second reactor now that they gotten the other one under control, the politics, damage control and everything. And they wanted to start up the second one so they could start making some money off it because it was just sitting there. It was a couple of $1 billion asset at the time, not making any money. And they went to start it up, and they got a new type of stress corrosion cracking never seen before in nickel-based superalloys called thiosulfate stress corrosion cracking. And as near as everybody could tell from heating up this thing, and you have, this was in the, what do you call it? It was one of the heat exchangers, I can't remember which heat exchanger, but basically, heat exchanger is a bunch of tubes inside a big pressure vessel, and if you heat it up, you'll end up in the transient stresses of heat up, you'll put tension on those tubes, okay? And they did, they got tension on the tubes, and as the reactor water, and they'd done everything to try to keep the reactor water purified and in good shape, but they had formed a type of polythionic acid, which it only forms in a reduced oxygen environment. It is due to some sulfur. I can't remember where the sulfur came from. But just looking at the transient thermal stresses, they only lasted for 30 minutes. And so they now had a $30 million loss of their heat exchanger. They had to build a whole new heat exchanger out of this nickel-based, I think it's Intel 625, I don't remember. But anyway, but no one had ever seen it. Babcock and Wilcox went off and did tons of research on this thing in the mid-80s, and you'll find plenty in the literature about this type of corrosion because it was a huge problem. And I was involved because the insurance policy of American Nuclear Insurers said, we have a corrosion exclusion, okay? And when the first day they announced this in the press, they said, we have a problem with stress corrosion cracking. And immediately their attorneys figured out you shouldn't be calling this stress corrosion cracking if your insurance policy has a corrosion exclusion, right? So the second day was now called stress-assisted cracking. Okay, they took the corrosion word out. And I said, well, what type of cracking is not stress-assisted? Okay, I mean, you have to have stress to have a crack. Okay, but anyway, that was one of my stupid questions. Okay. In any case, so they were all fighting of what does it mean? What does it mean to? What does corrosion mean? Is it a slow, gradual process? And what does slow, gradual mean? Is 30 minutes gradual or not? So this has nothing to do with science. It has to do with the wording, the layman's wording in an insurance policy. And so actually it went to arbitration or mediation and they finally settled it. But in any case, not until after a number of us paid enough money to put a couple of kids through college. Anyway, and in fact, I was like the 5th or 6th metallurgist for the insurance company. And one of them was Roger Staley, who was Ronald Tannisson's boss originally, okay, and was a big shot. He just passed away a couple of years ago. But Roger was there, and I said, well, why are you hiring me if you already have Roger? And they said, Roger's never available. He said, oh, okay. I said, well, you have this guy, Vashik Vitek, at Penn State, who was right there in Philadelphia where all this was being fought. And they said, yeah, but he can't speak English. Finally, they came down to me because I had a metallurgy degree. And I was a welder, but they talked corrosion. So in case Roger wasn't there, they needed someone to speak. Oh, they also had Charlie McMahon, who's a graduate of this department, had been head of the department at the University of Pennsylvania. But Charlie was on sabbatical one year. So they had all these reasons why they hired people and then they couldn't use them. So anyway, that's another piece of trivia. But it's a slow, gradual process. The metallurgists will call it the environmental degradation of material. So Ronald Tennyson, when he started here, and a few other people decided corrosion sounded sort of crude. And so they decided they really didn't work in corrosion, they worked on the environmental degradation of materials, right? Which you and I know as corrosion, okay, but it's a fancier name. So they gave it a fancy name to make it sound better. It's like Mike Seaman here when he first took over. When you make ceramics, you often use an organic binder of the ceramic powders. And the predecessors called it binder burnout, when you heated it up and burned off the polymer to leave the ceramic to make your part. And he decided that wasn't fancy enough sounding, so he called it binder pyrolysis. Okay, so you need to watch for these fancy names that mean nothing. Okay, the insurance adjusters will call it wear and tear. No one insures against corrosion. I mean, if the Navy could go get $1 billion insurance policy against corrosion, they would, because it costs you about $20 billion a year. Okay, and if you get someone else to pay for it, but the insurance policies call it wear and tear, and more specifically, they'll include fatigue and corrosion and things like that. Okay, material heading towards equilibrium. If you're a thermodynamicist, everything wants to go back to its most stable state, and unfortunately, metals are not in a stable state. The National Association of Corrosion Engineers claims in 2013 it's a $276 billion expense in the United States. I think they're up to $500 million now. Okay, inflation's really been running rampant in the last 4 years. Potential cause of failure. That's me, a failure analyst. You got to look at it and see if it was corrosion. And you, okay? I mean, I mentioned this guy who presented the problem in Yokosuka when they got into the seawater tanks, and they were all corroded, but it wasn't a type of corrosion anyone had seen before. That's one of the interesting things about corrosion. There are always new types of corrosion. I remember back in the early 80s, the reactor guys were finding bugs growing in the hottest part of the reactor. And these bugs were growing at 40,000 rad, okay? If you start looking at the biological damage, okay, they could replicate and repair their DNA faster than any living thing on the earth, okay? But I mean, ordinarily the radiation, and it had killed bugs for 20 or 30 years, but the bugs had evolved to where they could now replicate and reproduce it, correct, to repair their DNA. And so we were seeing bug-induced corrosion inside the hottest parts of the reactors, which was a problem. For the corrosion engineers, it's an opportunity, it's lifelong employment, and it's just something else we all have to live with. So when we talk about corrosion, there it is, there's a battery terminal. By the way, which terminal, positive or negative? Do you get all that crud? Actually, you don't get it on any of the terminals now, which we could talk about. But have you guys ever seen that? I mean, in car batteries, you don't see it, but maybe old tractor batteries or something.
Negative.
Positive. Positive. Corrosion occurs at the anode, which is positive. Okay. Anodic dissolution occurs at the cathode. Okay, so it's why you can't remember. I just remember that it's anodic. Corrosion occurs at the anode, which is positive. And you just have to memorize something, because otherwise, the cations are positive, anions are negative, corrosion occurs in the anode, which is positive. So, and to electrochemists, it all makes sense, but to the rest of us, it makes no sense whatsoever. Okay. So, and there's actually some interesting chemistry. When you take my soldering section, I'll actually talk about the corrosion that occurs there. And it actually has to do with the CO2 and moisture in the air. Okay? Without the CO2 in the air, you wouldn't get that. It's actually a lead carbonate that forms. And it takes time to form. It first forms a lead oxide, or lead hydroxide. I'll give it to you at that time. And that's the reason for that is it's a form of corrosion that you'll have on electrical circuits, okay, on circuit boards. Just same as your battery terminals. Okay, this is something that I put together 10 years ago, or whatever, when I started teaching this course, what are some of the basic principles that you need to learn about corrosion? And these are the principles that I think if you learn these principles, when someone comes to you, your chief engineer of the Navy, and they say, we've got this $1 billion corrosion problem, or right now they're saying, we got an LCS and we got cracking corrosion problems all over it, okay? And not just the LCS, the cruisers have it too, right? And you're gonna have to listen to a bunch of opinions because no one will be able to agree on how they would fix it. But you're the one who has to make the decision. So, first of all, most metals want to exist as either oxides or sulfides. That's where they came from in the ground. That's where, after millions and billions of years, they came to their equilibrium thermodynamic state, which was an oxide or a sulfide. And they want to go back to that, okay? And so you need to understand that that's where things are trying to go. Metals may possess inherent nobility or practical nobility, okay? Gold or platinum do not corrode like most other metals. And in fact, gold, platinum, silver, and copper, and I guess silver and copper, are basically the only 4 elements that are found in nature in their metallic state. Okay? So they can, copper is not in its most stable state as copper metal. Gold is pretty much in its most stable state. It's hard to corrode gold. Platinum, sort of in between, and silver sort of in between. But under certain geologic conditions, you can find metallic gold, platinum, silver, and copper. And that's inherent nobility. Okay, and we'll talk about that when we get to Courbet diagrams, which I actually think are useful ways of thinking about corrosion as opposed to the kinetics. Courbet diagrams are the thermodynamics of corrosion, what can occur, whereas Toffel equation and stuff is how fast does it occur. Okay, I mean, you know, balls can roll downhill, not uphill. That's the Courbet diagram. What can occur. Whether it will roll down the hill or not, or how fast it rolls down the hill, depends on lots of other complexities. And we're not going to get into that, okay? Because you don't have to know all those types of details. You can hire corrosion engineers to do that. Most metals possess practical nobility. Titanium is extremely corrosion resistant, okay? We use it in the human body, as I pointed out. And that's because it forms a stable oxide. And if it gets scratched, it repairs its oxide immediately in like 10 to the minus 8 seconds. And when you go through cold welding, you'll learn about the Langmuir, which is 10 to the minus 8 atmosphere seconds. How long does it take to form a monolayer gas on a surface? At 1 atmosphere, it takes 10 to the minus 8 seconds to fill up that surface. At 10 to the minus 8 atmospheres, it takes 1 second. Okay? I usually will break a piece of chalk in two and say, if I could put these 2 pieces of chalk back together within less than 10 to the minus 8 seconds, they would stick. But in fact, if I'm not quick enough, they'll get contaminated with moisture and other things. And that surface contamination will prevent them from rebonding. Okay? So it turns out, most things want to rebond as long as the surface doesn't get contaminated and as long as the surface is smooth. And that's actually 2 of the themes for 2 and 3 in the first couple of welding lectures. So practical nobility is 98% of all metals. Okay? They have a protective skin. Stainless steels, chromium oxide. Most of your high temperature nickel-based alloys, chromium or aluminum oxides. Very stable ceramics, but if you break through them, you start getting things like stress corrosion cracking. Okay? And there's various ways to break through them. Free oxygen or sulfur is required for corrosion. If you look, I got a picture of the periodic table we'll do here in a little bit. But if you look in that corner, the top left of the top right of the periodic table, you got your oxygen and sulfur, one above and below the other. And most of the rest of the periodic table just wants to react with something over that top corner, top right corner. And the ones that are most commonly available are oxygen and sulfur. Turns out sulfur, I showed you, passed around this thing, that's sulfidation at high temperatures. Has nothing to do with moisture or oxygen. It has to do with sodium and sulfur. And the sulfur comes from the jet fuel. And if you're a Navy aviator, where does the sodium come from? Seawater, right? You're surrounded by it. You can't get rid of it. And anyway, so you've got to have free oxygen or sulfur. And the way I explain that, a number of you guys have worked in reactor boilers, and you learn that you have to keep the oxygen out with hydrazine and other things to keep the oxygen out of the water. Why? For corrosion protection and control. Virtually all of the corrosion that occurs in a reactor, nuclear reactor, occurs on the transient startups, okay, or shutdowns. It doesn't occur when it's hot water, boiling steam, or boiling or hot water that has no oxygen in it, because it takes free oxygen. I always say if a fish can breathe, you're going to have corrosion. If a fish can't breathe, then you shouldn't get corrosion. And if you think about it, that explains why if you go to your home heating system, you can use steel pipes. Whereas in your potable water system, now we might use plastic, which I wouldn't recommend in most cases. I just rebuilt my house, an 85-year-old house, and they've got it down to the studs, and I took out all the copper pipe, and I said, no plastic pipe. There have been huge losses of environmental degradation of materials in plastic in water. And we'll talk about some of that. But I wanted copper. Why? Because copper will last for 1,000,000 years in water. It has in Michigan, okay, where they have native copper in the ground. So I paid the extra to have real copper plumbing, which most homes, new homes don't have nowadays. But you can still get it if you're willing to pay for it. And in fact, when MIT redid my office, copper plumbing. They don't use the plastic because they want something to be here 100 years from now. Okay? The plastic will probably last 30 years. And you may not live in that home for more than 30 years. But nonetheless, if you're really building something to last, you'll actually use copper plumbing. Copper plumbing's relatively new. We didn't really use it until after World War II. Before that, you might know what we use. We still use it in the Midwest some. If you're from the Midwest. Tended to use galvanized steel in the 30s and 40s in the Midwest. And you would have to replace it, just like on a nuclear or on a Navy ship. After 25 years, you got to replace the copper pipe. Okay? And you're running seawater through it. And we'll talk about how fast you can expect that general corrosion to go. But in general, if you're going to have free oxygen, and that's potable water, okay? It's got air in it. You're going to have something better than just steel. Why can you use steel in a boiler? Well, when you first put that steel in, and you have fresh water in there that's got oxygen, it actually starts to react with the steel. And it forms a different oxide in the reduced oxygen environment because the oxygen is being consumed. At 1 atmosphere, or 2/10 of an atmosphere of oxygen, 1 atmosphere of air, but at 2/10 of an atmosphere of oxygen and iron, you get something called Fe2O3, which as a metallurgist I sometimes call hematite. You call it rust, okay? And it's sort of orange or brown and stuff. But at 1/10 of an atmosphere of oxygen, or less, you will tend to form magnetite, Fe3O4, which has less oxygen. The iron-oxygen ratio is less in magnetite than it is in hematite because it formed with less oxygen available. And this is what you call black iron pipe. You actually form, it turns out the magnetite forms a protective scale that's better than paint. Okay? Now it can be scratched, and there could be other problems. But not a lot, you don't have a lot of scratching going on the inside of your boiler pipe, okay? So if you can keep the oxygen out, in fact, a number of years ago, 20 years ago, some people brought me some sprinkler pipes, okay? And most of your fire sprinkler pipes, actually today, most of them are plastic. In fact, I put a sprinkler system in my home when I redid it. Full fire sprinkler system. And I was surprised, I was looking at it this weekend. It only cost $21,000 for the whole house, which is the best bargain for the whole fire protection system. But I also learned that the fire chief in the town of Belmont he was impressed that I was doing it. He was very pleased that I was doing it. He also was nitpicking about everything because he tried to use the commercial standards for fire protection systems and make me impose those on me as a resident. And I had to go and get some National Fire Protection Association standards and point out to him that they have different standards for residences than they have for commercial buildings. Okay? But in any case, because he wanted to do a bunch of other stuff, which was not required unless I was a commercial building. In any case, they tend to use plastic pipe, and there are arguments, and we can go over that, whether plastic pipe or steel pipe is better for sprinkler systems. But in any case, the steel pipes cost more to install because you got to thread them. The plastic pipes, just throw some adhesive on there, and as long as you don't get the adhesive in the wrong place, you don't get environmental stress assisted cracking. Okay, but you can, and there are some major problems out there on some fire protection systems. In fact, one of the problems on the plastic pipe, it's not the plastic, but they interface with some steel pipe. And the steel pipe, they've sprayed an oil-based coating to keep the bugs down for microbiologically induced corrosion. And that coating on the inside of the steel pipes gets into the water system of this closed system and causes stress corrosion cracking of the plastic. And that's probably $1 billion problem around the country right now. Fire sprinkler pipes are cracking all the time because the steel pipes are contaminating the plastic pipes. So when you start mixing materials, you often end up with all kinds of problems that you didn't anticipate. In any case, we can use in a closed system, we can use iron pipes. In an open system, we have to use copper pipes. And the story I was telling, they brought me, it was like a 1-inch pipe, completely filled with iron oxide, hematite, this one. And they wanted me to do an analysis on it. They had this huge warehouse, 50,000 square feet, and the entire sprinkler system had hardening of the arteries. And I called up before I did anything, I said, "You guys had a leak in your system, didn't you?" He said, "Yeah, how'd you know?" I said, "Because I gotta have oxygen. You didn't have a closed system. You were continually bringing in through your leak." Yeah, they had a leak. It was about the size of a 1/4 inch, and they just had it running straight into a drain for 10 years. And for those 10 years, all that fresh makeup water was bringing in oxygen and corroding the inside of their steel pipes. And they said, "Well, what do we do?" I said, "You replace them all." They weren't very happy. And my bill was 1 hour of my time, right? Talking to them on the phone. But that was the answer. Because you don't get corrosion. Number 3, or number 4, which one is it? 3, free oxygen is required for corrosion. They filled up in 10 years their pipes because they didn't do the maintenance that was required to fix the leak. Okay? They were sorry about that. Okay. So tomorrow we'll hear from 2 of you, and then I'll continue on some of this and things. Okay? So it's sort of, in some ways it's disjoint, but I'm not going to teach you everything you need to know about corrosion in 6 hours. Okay?